My name is Brianna Curl, and I will be your moderator for today's webinar on high-density interconnect, addressing complex and dense PCB designs. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly during the webinar. With that being said, I want to thank you all for joining us for today's webinar and introduce you to our presenters, Jeff Keister and Sue Frederick. Jeff is a field applications engineer with over 40 years of experience in the printed circuit board field. His focus is on OrCAD, Allegro, CIS, CIP, and CAD-Sync. Sue has worked with the Cadence tools for over 25 years, both as a PCB designer and application engineer. Prior to joining EMA, she worked in post-sales customer support at Cadence, focusing on the front end of OrCAD, Allegro, and PCB SI flows. Jeff will be presenting, followed by the demonstration given by Sue. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Jeff.
Thanks, Brianna, and welcome everybody. So today we'll talk a little bit about the agenda, and we'll go over some stuff with high-speed design procedures, and then I'll turn it over to Sue, and she can show you how this can be implemented in the Allegro tool. So today we're going to talk a little bit about what HDI is, you know, why you want to use HDI, the different types of HDIs that are available, the pros and cons of HDI vias, high-density PCB layout, what is a micro via, and then of course we want to be able to talk about HDI costs, and then via fan out as well. And I've got a little bit of some guidelines that I think be a little bit helpful for everybody that's starting to use micro vias. So first thing, what is HDI? So HDI stands for high density interconnect. It's a printed circuit board with a lot more wiring that's designed inside of the board. So the density is very, very thick than the conventional boards. You're going to see a lot more chips on the board with 2,000 pin via VGA counts and things like that, and multiple layers. You're going to include fine features like signal traces, like down to 0.003, you know, or less, and you're going to be seeing things with laser drilled blind and buried via micro technology that's going to be available to you. And micro vias are going to allow us to use micro interconnects within the PCB, which is going to free up a lot of routing channels to be able to interconnect all the VGAs together. You're going to be able to use smaller diameter pad sizes, creating additional routing density. And you're also going to have extensive applications that you're going to be able to use when you're using HDI. So there's a lot of products that are going to be out there, things like cell phones, GPS, telecom, automotive, and military and medical companies are starting to get more boards that are much denser and require high density definition when we're going in with designing those circuits. So typically on an HDI board with the finer pitch VGAs, you're going to need things like smaller vias, which are going to be your micro vias, you know, whether they're mechanically or laser drilled. We'll have blind and buried or even staggered vias for layer transitions. Now, these vias have smaller aspect ratios than typically through-hole vias. So in order to use these vias with finer pitch components, the diameters are much smaller, which then eliminates the useful part of the complete depth throughout the whole design. You're going to have thinner traces that are used in HDI boards that are required to make connections to vias from each layer, as well as to have in-pad vias. And the thinner traces also allow higher trace density, thus the term HDI. Higher layer counts. HDI layer counts can easily reach anywhere between 20 to 30 layers when working with high density components and 2,000 pin or greater BGAs. You'll also have lower signal levels. So HDIs are not used for high voltage or high current designs. This is because the high field strength between the neighboring lines will cause a lot of ESDs, and high currents will cause excessive temperatures, you know, on the design. So you won't see so much of that in when you're dealing with high voltage and high current designs. When working with high pin count devices such as FPGAs, you're going to see a lot more of people using high pin count devices that are going to be in there. Traces are going to be made much smaller. They are routed closer together. Micro-vias are used to route signals throughout the inner layers. And not only that, but the component sizes are also going to be a lot. You're going to have the bigger BGAs, but you're going to have a lot smaller components. You might be even go into where you're using embedded resistors and capacitors inside of your designs. You're also going to be scaling down the size of the critical routing features to accommodate small components and packages with high pin counts. And then this is where your design tools are going to need to give you the freedom to define the right trace lengths and the right via types and the right stack-ups. So having the right design tool is very important because you're going to be using your constraints managers tools to help define what signals are going to be able to use micro-vias, what layers they're going to be able to route those on. So it's very important that you have a good constraint tool editor that allows you to design those circuits. So why do we do HDI? Well, one of the main reasons is because we need to be able to take things into much smaller products. We're miniaturizing things. The pitch is going to be far greater, and the features of the product are much greater. And we can do things cheaper with high density cost per connection. So we can get a lot more interconnects on our board using HDI technology. The performance is 1/10 of the parasitic of the plated through holes. We're going to have a lot fewer stubs, and we're also going to be able to improve the noise margins that we have between the inner layers. You'll also have a lower substrate weight because things are going to be a lot thinner using the HDI technology. So thickness and volume is going to be much greater. And you can see from these diagrams, like on the one where I have on the left side where we have via starvation, you've got a lot of through holes, and you can see that you don't have a lot of channels that you're able to route in. So by using micro-vias is going to free up those layers to where we can actually do a lot more routing into our internal layers. And then reliability with better aspect ratios with these vias and thinner dielectrics is going to be much greater than using the thicker material. So what is the micro-via? So micro-vias can either be blind or varied vias, as you can see in the diagram. Micro-vias are used for the interconnect between the layers of the high-density interconnect substrates. And this is important when you're wanting to be able to make your connections from your BGAs into your internal layers. And then when utilizing the micro-via structure, typically, like I said, you're going to have thinner dielectric materials, which will contribute to the higher reliabilities. So what are the pros of using HDI? You're going to have component space constraints, may force you to do via in pad, which is really nice, but it's going to be also a higher cost. You're going to have fine pitches, which are going to force you into using micro-vias because you've got no way to pull traces out from underneath those BGAs unless you do. And you've got EMI and EMC suppression and shielding may provide a cause for using HDI. So you want to be able to get a better signal on your traces by using those interconnects. Signal performance, such as RF or high speed, can create the case for HDI because you've got, maybe you've got HD or RF circuits that are located in a section of the board that you're going to need to be able to bring in more technology into the RF area. So this can drive HDI technology as well. And also large-scale integration, like we talked about with high pin counts of BGAs. This may be cost-effective with HDI methods to lower the layer counts with standard than what you have on normal board thicknesses. Plus, you're also going to improve power management, because of the thinner dielectrics. But what are the cons of using HDI? And this is important. Because there are a lot of cost factors in this. And the rule of thumb is, 10 to 20 layers is usually going to be what you're going to be designing with because you've got such high pin counts. Non-conductive via fill is going to be a problem in manufacturing. So this can cause some issues. So working with your manufacturer is very important. Via and pad can also cause some problems because of manufacturing. You want to make sure that those are completely filled and panelized. And then they cost more time to construct these. So there's a lot of steps that go into building your HDI boards. Testing of the circuits may not be accessible. This could be a problem as well, getting the electrical tests to the probes right to the pads. And repairs are always a problem when you're doing HDI. So it's very important that you try to get this done correctly the first time, because repairing designs can be really time-consuming and very costly. And then it takes a longer time to interconnect these designs. So as a PCB designer, routing HDI technology is going to take you a little bit longer to be able to connect all these lines internally, make sure that they're connected. So it's important that you have a nice CAD system that's able to help you with that. And the cost, of course, as speed and performance is increased, you're also going to find heat issues. And we all know that heat is not our friend on printed circuit boards. So voltages are going to have to come down to reduce the heat. And as the voltages come down, size and pitch are going to be reduced. So we want to make sure you can see that you're going to be getting a lot more components on the board being putting onto HDI technology. So we want to try to reduce all that. As performance went up, and so did the pin count goes up, of course that does. The results that you're going to have are smaller case sizes. You're going to see a lot smaller components onto the board, which is going to be a problem for assembly. You're going to have, like I said, the increased pin counts. You're going to have lower voltages also on those designs because you want to try to keep the heat down. And increased thermal connections between the inner layers that you're running your voltage on. A lot of times you won't be running any traces on your voltage layers. And then don't forget, it's going to cost, less, but people are going to want to have this done a lot quicker. And anybody that's laid out HDI boards knows that it's not a quick fix to be able just to jump right into HDI technology. So here's some standard configurations of some designs, and you can see what the cost is as you go in and add the different types of blind and varied vias. If you're going from layer 1 to layer 2, or layer 6 to layer 5, and then have a core via in the center of that, that's pretty much the standard configuration. But as you start to go into these other configurations where you can see that we've got blind and varied vias internally, that's going to be, like I said, it's going to take a lot more time manufacturing these designs because they've got to go through these layers, specifically one layer at a time, to build these up. So cost is going to be definitely an issue when you're dealing with this kind of technology. And something else that's important is being able to create boulevards when you're routing. So not very many of the CAD systems out there today are creating boulevards. It's nice that ours does. So we're able to create different kinds of fan outs when you're coming out of those huge BGAs. It's very important that you create channels for routing to be able to take those interconnects that are inside the internal area and be able to bring those out on different layers. So being able to fan out components in all kinds of different methods, whether it's cross-shaped channels or L-shaped channels or diagonally shaped channels, is going to help you with being able to route in and outside of your BGHs. And you're definitely going to get into about a lot higher pin count, finer pitch components. So you're going to be dealing with 3 and 4 mil lines when you're routing internally and underneath these BGAs. And then maybe once you pulled it out from those BGAs, you can go to a thicker line width. But you're definitely going to have a lot finer pitch components, and you can see here as we've got down to 50 millimeters, pitch components. And that starts to become pretty tiny when you start laying these boards out, which means you're really going to be needing to deal with your manufacturers. So some of the guidelines that are really important is, you should always, first thing, always check with your manufacturers. This is a general rule to always be planning, your designs. Give them a call, tell them what you're thinking about doing. Not all manufacturers have the same capabilities in your area. You might need to check, where the best manufacturer is, work with your team in purchasing to be able to get conversations with those manufacturers to find out their capabilities, because you want to make sure that you've created this design and you want to make sure it's definitely manufacturable. Keeping track of spacing between traces and pads is going to be very important. So a constraint manager is going to be very important to you while you're designing. Setting up those constraints with your engineer are going to be, and your manufacturing are going to be very important, and that's something that we can help you with the Allegro tool. And then don't use staggered vias if you don't need to use those. The whole point of HDI routing is to provide such a space as possible for routing, on the surface or the inner layers. While it might be tempting to stack across the entire span of the substrate, don't take up the extra space unless you really find that that's necessary. And then opt for fewer layers. So high layer count boards can bring assembly steps and manufacturing costs, up. If you follow these, these guidelines, you're going to definitely reduce your cost per board. One thing that's major, and I stress this to everybody, is don't forget about signal integrity when working with HDI boards. Any HDI layout, that you're going to design, and with high frequency guidelines, you're going to, even RF, you're going to want to be able to use signal integrity and set the rules up for that. So it's very important that you're using, first of all, dealing with your manufacturer. One of the utmost, I can't stress that enough, having a constraint manager that's going to be able to handle the constraints so that you can implement those constraints into your design tool, and then the DRC can follow those constraints. And then second, or the third thing is signal integrity. Make sure that you're running signal integrity on these designs, because the last thing that you want to do is really do a spin on this design without having done any kind of signal integrity. Sue's going to give you guys an idea of using the Allegro tool, how this works best with our tools, and how we can help you guys to achieve a non-spin design using the Allegro tools.
Thank you, Jeff. And 63% of you had agreed that ensuring your design is manufacturable is one of the biggest challenges. So that just stresses the importance of communicating with your manufacturers to make sure that you know what you can and cannot do when designing these high-density PCBs. So with that being said, I'm going to pass the screen over to Sue, and she can start our demo.
Okay, thank you, Brianna. Okay, so what I'm showing you today is it's in Allegro PCB Editor with the miniaturization option. This option allows you to actually use microvias in your design and constrain them as a separate element in the board database. And what I'm showing here is just this is a 1 millimeter pitch BGA that I've routed out according to how Xilinx has recommended fanning it out. So here you can see the pad size is a 16 mil pad size and the pin pitch, the via pad size 24 mils. With this breakout, you can actually just use standard technology. So you don't need micro vias, you don't need to use blind and buried vias. You can use 5 mil traces and 5 mil spaces. And so this actually requires 4 layers to break out. So here's the top layer, and then each of the signal layers underneath. It's all broken out, all the pins are broken out. Now, really when you start doing an HDI design, you really need to decide at the beginning of the design whether you're going to make it in an HDI design. And if you are using microvias, you actually have to set up your stack up so that you can use them. Your aspect ratio of the microvias needs to be more of a 1-to-1 drill size to the thickness that the via is spanning. This is obviously not a real stack up. I'm just showing it here, but just you need to set your thickness of the of your dielectrics between your microvia layers so that you can drill through those and have your correct aspect ratio. One thing that you can use to help out on the internal layers is to use your pad suppression. So if any unused vias that are on the internal layers, if they're not connected on those layers, you can suppress those the pads on those vias by coming in here. You have to set it up in the pad stacks and set it up in the stack up whether or not you want this layer to suppress the vias or the pins, and then come down and actually turn on the dynamic unused pad suppression. And then when you go to each layer now, you can see here, these are showing the hole sizes, whereas the pads are only showing for any of the pins that are connected, on any of the vias that are connected on that layer. So it actually gives you a little bit more room to try to route through there. Things are a lot different though when you start getting into the finer pitch BGAs. This is a 0.4 millimeter BGA, and you can see everything is a lot tighter. It's harder to break out of here. You need to go to the microvia technology in order to break this out. You can't get any traces on the top layer. You can't get anything through the pins, so you can just route your outside layer or outside row of pins on the outer layer. And then start, as you break out your inner layers, then you start just going in another row. So your second row of pins is going to break out on your next layer, third row on the next layer, and so forth until you break everything out. Different things to think about when you're breaking out the BGA. You have to think about your pin count of the device. Obviously the pitch of the pins, because as the pitch decreases, then you're going to have less space to try to break those traces out from that BGA area. The BGAs have different patterns to them. Some have pins in the middle, some don't. As Jeff had mentioned, always go to your manufacturer when you're trying to determine what your pad sizes need to be in traces in these areas. So the microvias are also useful in other areas, not just for the BGAs, but you can also use them on fine pitch components, where here there are actually using a via in pad for these pins. If I didn't use that and just used mechanical vias to route out from here, then it would take up a lot more room and it would close up a lot of routing channels. So the microvia technology is very handy for all your fine pitch parts on the board. Now, I just wanted to show you some of the functionality of what you can do in the tool to work with the microvias and the stacked vias and staggered vias. Now, all of the via distances and the stacking, it's all controlled in Constraint Manager, and I have constraints set up in here. I'm not going to go through all of them, but in terms of setting up the constraints to be able to handle the blind and buried vias and the microvias, one of the first things you can do is make sure that you have the correct vias being used in your physical constraint set. So I have, let's say for staggering vias, in here I'm just selecting the different vias that I want to use when routing this net or any nets with this constraint set. So these are, they're all blind and buried vias. So you have one going from layer 1 to 2, then 2 to 3, and then there's a core via. So the outer ones are microvias. So 6 to 7, 7 to 8, 1 to 2, 2 to 3 are all microvias. And the core isn't, it's just a buried via. And this is how all of my physical constraints are set up in this next area that I'm going to show you. So in addition to using your physical constraints, you can also use same net spacing constraints to control how microvias are connected or to other microvias, how far away they need to be from the core via, things like that. This is just a little diagram that shows how you can configure your vias inside the tools. This one on the left is just an overlap or inset via. So you have your green core via, and then the microvias are actually offset. They're overlapping. The pads are overlapping on them. And the next one is where your microvias are stacked on top of the core via. And then you have one where only your microvias are stacked. The core via, they're staggered from the core via. And then you just have everything where everything is staggered. So I'm going to show you what these look like when you start routing them. So this first one is going to be a staggered via. So if I start routing this, then what I can do over in my options pane is set up my working layers. So I'm using a working layer model, which might be a little different than what you're used to using. And what this is going to do, once I double click to drop a via, it's going to bring up a form and say, where do you want to route to? So I want to try to get this to the bottom of my board using the blind and buried vias that I've set up. So as you can see here, the way my constraints are set up, it's allowing the micro vias to stagger from each other. So I can place one down, then next on there, it's getting to the next via that it finds to take me down another couple of layers. So now it's the core via attached to my cursor. I can place this down and then back to my micro vias. And then now I'm down to the bottom of the board. So you can see here how I've gotten from the top to the bottom of the board using the blind and buried vias that I have set up. This next one is going to be stacked micro vias. So the two micro vias will be stacked here, they'll be stacked here, and then they'll be staggered from the core via. So once again, I'm going to try to get down to the bottom layer. And then now you can see I have my two vias, micro vias got stacked. So now put the core via down and then the next set of stacked micro vias, and then I'm down to the bottom. So you can see the difference in the two of how they look here. This next one is going to be stacking the micro vias and the core via. So now everything, it's just all stacked together. And then the last one is just going to show the overlap. So your pads are going to overlap on the micro vias. You can see how that it's set up so that the pad edge is actually next to the hole on those micro vias and the core via. So here, as I place it down, and I can place it down here if I want to. So this just shows the different techniques that can be used when you're routing with the blind and buried vias in the board to easily get from one layer to another. And then showing this in 3D, I can bring up the 3D canvas. And you can see how these vias are now showing in here. If you want to see a particular net there, I can highlight that staggered via pattern in the 3D canvas. So you can see how it's all staggering and getting down to the bottom of the board. So just kind of a handy way of looking at your vias in the in 3D. So one other thing that you can do here is use via structures to fan out your BGAs. So if you have a particular via structure that you've set up, maybe you have something for differential pairs where you want to have a particular void in the via breakout on that diff pair, and you want to use it for multiple diff pairs, you can actually create a via structure for this. I'm just going to do a simple one, and I'm going to create a stacked via on one of my pins. So I'm just going to go down to layer 3. So now I just have a stacked via. And one thing I wanted to mention was that if you look inside these the blind and buried vias, you can see some of them have dashes and some of them have colons in them. So the ones with the colon, they just that represents a single via spanning multiple layers, where the dashed vias are showing a stack of vias. So you can see 1 to 8, it's a stacked via going from layer 1 to the top layer to the bottom layer. So you know that's a stack of vias. Just an easy indicator to see that. So here I have my stacked vias. There's 2 vias, 1 to 2 and 2 to 3. And what I want to do is use this same via structure to fan out the rest of my BGA. So I can create a via structure, come in here and do structures, create. I just give it a name. And then I can draw a window around here. It's going to ask me to save it. I'm going to save it out to an XML file, which I could use in another board. So I can make these via structures and use them in another board to fan out components in there as well. And then I can use it to just go into the create fan out. And over here, I want to route from the top to layer 3. And then I can say, use a standard via structure. And I want to use the fan out that I just created. And what I can do is just click on here. And now I've just fanned out that entire BGA with that via structure of the stacked vias. So it's just an easy way to get your vias in there once you already have your via structure created. Important things to take away is when you're breaking out your vias, check with the component manufacturer to see if they have a recommended land pattern, recommended pad sizes, things like that. So start there, work with your board manufacturer to see the sizes of vias and traces that they can handle on each of the layers, get your stack up set up, and then before you start routing, don't resist the urge to route your interfaces first on a BGA. Do your fan out first to make sure that you can get everything out of that component, out of that BGA area. Because if you go in and you start routing an entire interface and then come back and realize you can't get some of these other signals out from the center of your BGA, then that's a lot of work that you've wasted. And so when you're doing an HDI design, just remember there are a lot of things to take into consideration. Using the micro-Vs is going to give you more space in the design, but there's going to be an additional cost. So you have to weigh the cost versus the size of your design. That's all I had.
And now we can begin the Q&A. So if you have any questions, feel free to ask them within the questions pane. So our first question, it seems like there is some confusion along the lines of when to use the staggered versus stacked vias and why you would use one versus the other. Could you guys clarify that a bit?
Yes, I mean, using stacked vias is really something I guess I can emphasize that you want to work with your manufacturers when you're using stacked vias. There is the new latest IPC reliability testing that's been put out where some people are saying that stacked vias are, I mean, I don't want to say that don't use them. They do create a little more space and manufacturing can be an issue for them, but definitely want to emphasize working. If you're going to go with stacked vias, you want to work with your manufacturer. You want to find out what the costs are going to be generating that. But it's not whether to use one or the other. It's just a matter of choice. But I would say definitely work with your manufacturers to find out which is the best way for them to manufacture your designs. Sue, do you want to add anything to that, or?
No, it's like you said, a trade-off between cost and how much room you need on the board.
Thank you.
Somebody did ask a question on what level of Allegro are you featured in, so we might want to answer that question of what you need when you're in Allegro, Sue.
Yeah, this is the miniaturization option. That's the one that's going to get you the separate micro via as a separate element in the database. So it's separate than a blind and buried via. If you don't have the miniaturization option, then everything is considered a blind and buried via.
Let's see what other questions we have here. Here's an interesting question. Many high pin count processing ICs have high current power pins. Is it best practice to stick to standard mechanical vias for these pins?
I think some of it's going to depend on what your if it's a fine pitch part, I'm not sure if you can use the mechanical vias in that area.
Okay, so it basically comes down to what space is available.
Mm-hmm.
Another question here. Will there be an auto breakout tool inside Allegro to automatically add the breakout pads?
There is an auto interactive breakout tool in the design planning option that helps you with breaking out of the pads. Kind of in terms of breaking out an interface where you can break out one end, break out the other end, and then route the trunk to help you route between them.
Okay, let's see. What is the size of a micro via?
So the IPC defines it as a via with a diameter that's less than 6 mils and a pad that's less than 13.8 mils.
Okay, thank you. If HDI designs are more expensive to build, why should I use them?
You have to use them with the finer pitch components, but HDI designs can actually reduce your layer count, which will reduce your board size, and it could reduce the weight and the size of your electronic products out there. So if you're looking to reduce the size, then you want to go with HDI.
Let's see if there are any other questions.
Well, here's the last one that we could get is what's the most widely used BGA breakout technique? You know, that really depends on your BGA, where your pins are located and where they're going to feed to the other components. So that's kind of a trial and error thing when you're going for the BGA fan out. So depending on where all your blocks of pins are going to be talking to the external components outside. So I like the diagonal one the best. It gives me the most options for being able to pull out of there, but it really depends on your BGA.
We have someone here asking for like recommendations on specs and materials, and again, that's probably best to be followed up with your manufacturer and who's going to be actually making your board. They would be able to provide that information to you.
Somebody also asked for a favorite PCB supplier. I don't have a favorite, but I'm sure you can find them online.
Yeah, it all comes down to what exactly you are trying to create. Some suppliers are better at doing other things than others, so
right.
It's best just to call around and check in what their capabilities are.
I got one thing that Happy said. Happy's been in the business for a very long time, very well respected in the business. He says that there is a free HDI handbook out there that you can download. So I don't know where you can get that is, but there is an HDI handbook. You can probably Google for that and give you the guidelines for that. So thanks for pointing that out, Happy.
Yeah, thanks. We'll see if we can actually include that handbook in our email that we'll send out as a resource people have some access to. Yeah, with that, I guess we can wrap up our Q&A. If there were anyone who we weren't able to answer your questions immediately, we will follow up with you all individually. And you can always reach out to us at EMA at info@ema-eda.com for more information, or always check out our resource page also. I want to thank you all for joining us today, and just a reminder, we'll be sending out an email with the presentation and slides. And before we sign off, I'd like to inform you of our next webinar, which will be based on our new product called CAD Sync. So keep an eye out for the information on that webinar. And thank you all for joining us, and thank you, Sue and Jess.